chapter 8. Let's do the work. Alright, so chapter 8, section 5, question 29. Alright, so this is a sample question. This is the original question. Express the integrand as a sum of partial fractions and then evaluate the integral. This is the integral negative 4x squared over x to the 4 minus 1 dx. So we are going to first express the integrand as a sum of partial fractions, and then we are going to evaluate the integral by using these partial fractions, and the answer is given as follows. Okay, now I'm going to give you a similar question here. Look how similar this is. X squared over x squared minus 1. Okay, we are interested in finding the integral of this by using integration by partial fractions. First thing we do, x squared over x to the 4 minus 1. We are going to write ab cx plus d over the terms. How do we do that? We first factor x to the 4 minus 1 out. You can factor it out like x squared plus 1, x minus 1, x plus 1. Then we are going to write it as a over x plus 1, b over x minus 1, and cx plus d over x squared plus 1. You remember this is the irreducible factor, so we have to write on top cx plus d. Then we are going to equate the denominators and get rid of the denominators. On the left hand side we have x squared. Coefficient of a is x minus 1 x squared plus 1. Coefficient of b is x plus 1 x squared plus 1. And cx plus d, x minus 1 x plus 1. We have that. Then we factor out, we gather the like terms, for example, x cubed terms, x squared terms, x terms, and the constant terms together, and the coefficients of all these terms are given as follows. We gather them and we compare this with x squared. X squared has a coefficient 1, so we look at the coefficient of x squared, which is negative a plus b plus c. It has to be 1. And the rest is going to be all 0. So a plus b plus c is equal to 0, which is the coefficient of x cubed is 0. A plus b minus c is equal to 0, which is the coefficient of x. And the constant term is equal to 0 because we don't have a constant term on the left hand side. Then we solve 1, 2, 3, 4 equations together. And you first add equation 2 and equation 4, which is going to give, adding equation 1 and equation 3 is going to give us 2a plus 2b is equal to 0. Adding equation 2 and 4 gives us negative 2a plus 2b is equal to 1. Then we are going to add these two up, and this is going to give us 4b is equal to 1, then b is equal to 1 over 4. And by using one of the two equations, then we get a is equal to negative 1 over 4. And then we are going to use this equation to get, I think, let me see, this equation or that equation, doesn't matter. You're going to get d is equal to 1 over 2. So we have a, we have b, we have d. In order to find c, we have to use this equation, put everything in, and we get c is equal to 0. Then this integrand, which is x squared over x to the 4 minus 1, can be written as a, which is negative 1 over 4 over x plus 1, b, which is 1 over 4 over x minus 1, cx plus d, which is 1 over 2 over x squared plus 1 dx. Now we integrate this term by term. The integral of the first, the integral of the second term, integral of the third term. And the first term is easy, it is natural log absolute value of x plus 1. The second one is easy, natural log of absolute value of x minus 1. Don't forget the coefficients here. This is 1 over 4, this is negative 1 over 4. And then the last one is arctangent, right? Arctangent x, don't forget the 1 over 2 in the front, plus the constant c. That's how we find it. Now, I recommend you to try this out and try to get the answer as follows. Okay, you just first write it in terms of partial fractions like that. You're going to find a, b, and cx plus d. And then you're going to integrate this, and when you integrate this, you get ln x plus 1. When you integrate this, you get ln x minus 1, absolute value of the two. Since there's a difference, you're gonna get it as the quotient, and this is gonna be arctangent x, and don't forget the 2 and plus c next to it. You are good to go. All right, and the next question, I'm gonna skip this question. Okay, and I'm gonna skip this question too because I didn't talk to you about the Simpson's rule. I put it in here, and let's see. Okay, And the next question, 59. Okay, they're asking performing a test to determine if this integral is convergent or not. Okay, and but they first give you some hint. So they are asking you first, is this convergent? If this convergent, I mean, can you find the exact value? Yes, actually we do, right? This is power rule, 4x to the -3, but you increase the power by 1, 4x to the -2 over -2. If you evaluate that, you're gonna get 0 minus 4 pi over 3 squared, right? You get that like that. So you find a finite value. This is reasonable because look at the p-test. P-test says whenever power of x is bigger than 1, this is convergent. You're going to get a finite value, and we did. And then afterwards you look at this, you compare this integral with this integral. And we are going to show that this integral is actually less than this integrand. This integrand is less than this integrand. Then the integrals are going to be ordered as well. Since this is, I have to go down. Let's see. Since this integral is convergent, then this integral is convergent too, by comparing the two. Okay, and this is the answer, and it converges. Let's look at a similar question here. Look at that 59. The function is similar to plus cosine x over x, but in this case the answer is divergent because of the p-test again. Observe that actually 1 over x is less than or equal to 2 plus cosine x over x, right? Because cosine x bigger than -1, 2 plus -1 is 1, so 1 over x is actually less than or equal to this value. We order that, and then we know the integral of from pi to infinity dx over x is divergent because of natural log. This is the natural log. From pi to b goes to infinity. This is going to be ln b minus ln pi. Ln b is going to be infinite minus a number is an infinite. So this is a divergent integral. And observe that this integral is bigger than this integral. So if this integral is bigger than a very large number, then it's very large as well. So it is divergent as well. So we call direct comparison test. So we compare this function with this function where this integral of this is divergent, then this is going to be divergent as well. But in our solution here, we compare it with a convergent integral, and we show that this integral is less than this convergent integral, and we are good to go. Okay, and it's the end of it. Thank you.